Hello students, today we will be discussing on the topics equilibrium state and open and closed systems. Here we will learn what is meant by equilibrium state, how standard free energy is related to the equilibrium constant, how concentration of reactants and products affect the free energy changes in a reaction. We shall also learn about open and closed systems in thermodynamics. We all know that living cells and organisms must perform work to stay alive and to reproduce themselves. The synthetic reactions that occur within cells, like the synthetic processes in any factory, require the input of energy. In the course of evolution, cells have developed highly efficient mechanisms for coupling the energy obtained from sunlight or fuels to the many energy-consuming processes they must carry out. The molecules and ions contained within a living organism differ in kind and in concentration from those in the organism's surroundings. Once an organism has reached maturity, it maintains a constant composition in the face of constantly changing surroundings. Although the characteristic composition of an organism changes little through time, the population of molecules within the organism is far from static. Small molecules, macromolecules, and supramolecular complexes are continuously synthesized and then broken down in chemical reactions that involve a constant flux of mass and energy through the system. Let's take an example. The hemoglobin molecules carrying oxygen from your lungs to your brain at this moment were synthesized within the past month. By next month, they will have been degraded and entirely replaced by new hemoglobin molecules. The glucose you ingested with your most recent meal is now circulating in your bloodstream. So before the day is over, these particular glucose molecules will have been converted into something else, carbon dioxide or fat perhaps, and will have been replaced with a fresh supply of glucose so that your blood glucose concentration is more or less constant over the whole day. So the amounts of hemoglobin and glucose in the blood remain nearly constant because the rate of synthesis or intake of each just balances the rate of its breakdown, consumption, or conversion into some other product. The constancy of concentration is the result of a dynamic steady state, a steady state that is far from equilibrium. Maintaining this steady state requires the constant investment of energy. When the cell can no longer generate energy, it dies and begins to decay towards equilibrium with its surroundings. So, living organisms exist in a dynamic steady state, never at equilibrium with their surroundings. So, cells are isothermal systems. They function at essentially constant temperature and also function at constant pressure. Heat flow is not a source of energy for cells because heat can do work only when there is a difference in temperature. The energy that cells can and must use is free energy, described by Gibbs free energy function, G, which allows prediction of the direction of chemical reactions, their exact equilibrium position, and the amount of work they can, in theory, perform at constant temperature and pressure. Heterotropic cells acquire free energy from nutrient molecules, and photosynthetic cells acquire it from absorbed solar radiation. Both kinds of cells transform this free energy into ATP and other energy-rich compounds capable of providing energy for biological work at constant temperature. The free energy change, or delta G, provides information on whether a reaction will occur spontaneously or not. Number one, a reaction can occur spontaneously only if delta G is negative. Such reactions are said to be exergonic. Number two, a system is at equilibrium and no net change can take place if delta G is 0. Number three, a reaction cannot occur spontaneously if delta G is positive. An input of free energy is required to drive such a reaction. These reactions are termed endergonic. And number 4, the delta G of a reaction depends only on the free energy of the product, that is the final state, minus the free energy of the reactants, which is the initial state. The delta G of a reaction is independent of the path or molecular mechanism of the transformation. The mechanism of a reaction has no effect on delta G or free energy change. For example, the delta G for the oxidation of glucose to carbon dioxide and water is the same, whether it occurs by combustion or by a series of enzyme catalyzed steps in a cell. Number 5, the delta G provides no information about the rate of a reaction. A negative delta G indicates that a reaction can occur spontaneously, but it does not signify whether it will proceed at a perceptible rate. Now let's look at the relation between equilibrium state, equilibrium constant, and standard free energy. The standard free energy change is directly related to the equilibrium constant of a reaction. Let's see how. The composition of a reacting system, which is a mixture of chemical reactants and products, tends to continue changing until equilibrium is reached. A chemical mixture at equilibrium is in a stable state of minimal free energy. At the equilibrium concentration of reactants and products, the rates of the forward and reverse reactions are exactly equal, and no further net change occurs in the system. And we also need to be able to determine the free energy change, that is delta G, for an enzyme catalyzed reaction to know whether the reaction is spontaneous or an input of energy is required. To determine this important thermodynamic parameter, we need to take into account the nature of both the reactants and the products as well as their concentrations. Let us consider a reaction where A plus B is converted to C plus D. In this reaction, the equilibrium constant is given by KEQ equals to the concentrations of C into the concentration of D by the concentrations of A and B, where A, B, C and D in square brackets are the molar concentrations of the reaction components at the point of equilibrium. So, the concentrations of reactants and products at equilibrium define the equilibrium constant, which is KEQ. When a reacting system is not at equilibrium, the tendency to move towards equilibrium represents a driving force, the magnitude of which can be expressed as a free energy change for the reaction delta G. The delta G of this reaction is given by delta G equals to delta G naught plus RT ln concentrations of C and D divided by the concentrations of A and the concentration of B, in which delta G naught is the standard free energy change, R is the gas constant, T is the absolute temperature, and A, B, C and D are the molar concentrations or activities of the reactants. Let's take this as equation number 1. Delta G naught is a free energy change for this reaction under the standard condition, that is, when each of the reactants A, B, C and D is present at a concentration of 1.0 moles for a gas. The standard state is usually chosen to be 1 atmosphere. Thus, the delta G of a reaction depends on the nature of the reactants and on their concentrations. A convention has been adopted to simplify free energy calculation for biochemical reactions. The standard state is defined as having a pH of 7. Consequently, when hydrogen ion is a reactant, its activity has a value 1, which is corresponding to a pH of 7. The activity of water also is taken to be 1 in these equations. So the standard free energy change at pH 7 is denoted by the symbol delta G naught prime. The relation between the standard free energy and the equilibrium constant of a reaction can be readily derived. This equation is important because it displays the energetic relation between products and reactants in terms of their concentrations. So at equilibrium, delta G naught equals to 0. So equation 1 then becomes 0 equals to delta G naught prime plus RT ln concentrations of C and D by the concentrations of A and B. And so delta G naught prime equals to minus RT ln concentrations of C and D by the concentrations of A and B. Since the equilibrium constant under the standard condition KEQ is defined as K prime EQ equals to the concentrations of C and D by the concentrations of A and B. Substituting equation 4 into equation 3 gives delta G naught prime equals to minus RT ln K prime EQ, which can be converted to delta G naught prime equals to minus 2.3 RT log of base 10 K prime EQ. This can be rearranged taking the anti-logarithm, which is K prime EQ equals to 10 to the power minus delta G naught prime by 2.3 RT. Thus, the standard free energy and the equilibrium constant of a reaction are related by this simple expression. We can also say that the standard free energy change of a chemical reaction is simply an alternative mathematical way of expressing its equilibrium constant. From this expression, it is clear that when K prime EQ, which is the equilibrium constant, is less than 1.0, delta G naught prime is negative and the reaction goes in forward direction. When K prime EQ is 1, the standard free energy change, delta G naught prime, is 0 and the reaction is at equilibrium. When the equilibrium constant, K prime EQ, is greater than 0, then the free energy change, the standard free energy change, is positive and the reaction proceeds in reverse. However, we must be careful in distinguishing between the free energy change and the standard free energy change. Each chemical reaction has a characteristic standard free energy change, which may be positive, negative, or 0, depending on the equilibrium constant of the reaction. The standard free energy change tells us in which direction and how far a given reaction must go to reach equilibrium when the initial concentration of each component is 1.0 moles. The pH is 7.0, the temperature is 25 degrees Celsius, and at what atmospheric pressure. Thus, the standard free energy is constant. It has a characteristic unchanging value for a given reaction. But the actual free energy change, delta G, is a function of the reactant and product concentration and of the temperature prevailing during the reaction, which will not necessarily match the standard conditions as defined earlier. Moreover, the delta G of any reaction proceeding spontaneously towards the equilibrium is always negative. It becomes less negative as a reaction proceeds forward and is 0 at the point of equilibrium, indicating that no more work can be done by the reaction. So students, that was all about equilibrium constant of a reaction and its relation with the actual free energy change and standard free energy change of a reaction. Now let's look at open and closed systems. Let's try to understand what open and closed systems are. In thermodynamics, the system is a region of the universe that we choose to focus our attention on. The rest of the universe constitutes our surroundings. According to the conventional definitions, an open system is one that can exchange energy and matter with the surroundings, while no flow of energy or matter between an isolated system and the surrounding is possible. A closed system may exchange energy but not matter with the surroundings. For example, the contents of a vessel on a stove with its lid tightly closed is an example of a closed system, as no mass can enter or leave the vessel, but heat can be transferred to it. So when the lid is removed, then it becomes an open system as steam leaves the vessel. A perfectly insulated, rigid and closed vessel is an example of an isolated system, as neither mass nor energy can enter or leave the system. The reacting system can be defined as a collection of matter that is undergoing a particular chemical or physical process. It may be an organism, a cell, or two reacting compounds. The reacting system and its surroundings together constitute the universe. In the laboratory, some chemical or physical processes can be carried out in isolated or closed systems in which no material or energy is exchanged with the surroundings. Living cells and organisms, however, are open systems because they exchange both material and energy with their surroundings. Living organisms derive energy from their surroundings in two ways. Number one, they take up chemical fuels such as glucose from the environment and extract energy by oxidizing them, or they absorb energy from sunlight. Living systems are never at equilibrium with their surroundings, and the constant transaction between system and surroundings explain how organisms can create order within themselves while operating within the second law of thermodynamics. That is, living organisms preserve their internal order by taking from the surroundings free energy in the form of nutrients or sunlight and returning to their surroundings an equal amount of energy as heat and entropy. So now we have come to the end of today's session. Let us quickly summarize what we have learned today. Living organisms exist in dynamic steady state, never at equilibrium with their surroundings. Second, the free energy change or delta G provides information on whether a reaction will occur spontaneously or not, but not the rate of reaction. Number three, a reaction is said to be at equilibrium. The rates of the forward and the reverse reactions are exactly equal and no further net change occurs in the system. And number four, the standard free energy and the equilibrium constant of a reaction are related by a simple expression K prime EQ equals to 10 to the power minus delta G naught prime by 2.3 RT. So when the equilibrium constant is greater than 1, the standard free energy is negative and the reaction goes in forward direction. When the equilibrium constant is 1, the standard free energy change is 0 and the reaction is at equilibrium. And when the equilibrium constant is greater than 0, the standard free energy change is positive and the reaction proceeds in reverse. And lastly, an open system is one that can exchange energy and matter with the surroundings, while the closed system may exchange energy but not matter with the surroundings.